So this next section, we're going to focus on the conjugates themselves and the ions. Again, my terminology is going to be a bit different here. I want to use the words conjugate acid that comes from bases and conjugate bases that come from acids, rather than doing all this weak salt, strong salt, blah, blah, blah stuff. Okay, hope that's okay with you all. I just think conceptually it makes much more sense. So given the following acid ionization constants, in other words Ka, what is the order of increasing base strengths of the conjugate bases? Okay, well, let's order them out in terms of increasing K. So HCl was the weakest, and then HClO, and then H2PO4, and finally of the ones listed here, HClO2 is the strongest of the acids, just listing them out in the values of K. Okay, so therefore HCN, weakest of these acids because it has the smallest K value, HClO2, strongest of the acids because it has the highest K value. Now let's think about the conjugate bases, Cn minus, ClO minus, HPO4 2 minus. Make sure you see that the conjugate base of H2PO4 minus is HPO4 2 minus, and then ClO2 minus. Okay, well, acids and their conjugate bases are inversely strong. So in other words, the stronger the acid, the weaker the conjugate base. So going down this list of the acids, we increase the acid strength list, so we would decrease the base strength. So thus, ClO2 minus is the weakest base, Cn minus is the strongest base, because HCN is the weakest acid and HClO2 is the strongest acid. So thus increasing base strength. ClO2 minus is the weakest because it came from the strongest acid, then HPO4 minus, then ClO minus, and finally Cn minus is the strongest base because it came from the weakest acid. Very, very important concept, that inverse relationship of the strength of acids and conjugate bases. So let's apply it again. Given the following Kb values, identify the strongest acid of those given. So here's all these Kb values for these bases. Okay, now again, let's order them in order. So the CH3NH2 has got the highest Kb, so it's the strongest of the bases. Okay, C6H5NH2, C3.8 times 10 to the minus 10, so that is the weakest of the bases. Okay, so that's the base strength going up. Now let's write those out as their conjugate acids, so we just add H plus to all of them. This is where some of those formulas can get fun, but just every NH2 becomes NH3 plus, NH3 becomes NH4 plus, N becomes N plus, and so on. Okay, now because that was the order of strength of increasing base, it's the same order but of decreasing acids. So therefore the strongest acid is going to be C6H5NH3 plus because it comes from the weakest of the bases. Now we'll take it to another level. I'm giving you pKbs. So here's a whole bunch of bases where they're pKbs. And I want the weakest acid from those in the list of the answers. Now, if you look at all of these bases, their conjugate acid is indeed listed here. So C5H5N, that's the base, conjugate acid, C5H5NH plus. C2H5NH2 is the base, conjugate acid, C2H5NH3 plus. NH3 is the base, NH4 plus is the acid. C6H5NH2 is the base, C6H5NH3 plus is the acid. And then sneakiness at work here, N2H4 is the base, so the acid should be N2H5 plus, which is written as its little structural formula here. But essentially, regardless of sneakiness and order, here's bases for which we know the pKbs, here's the acids. Now let's think about some relationships here. First of all, Kb. Well, the bigger the Kb, the stronger the base. Okay, so if you've got a couple of bases, the one with the bigger Kb is the stronger base. But remember our relationship that as the base gets stronger, the acid gets weaker. So as the Kb goes up, the strength of its conjugate acid goes down. But we're not looking at kb's here, we're looking at pkb's. Well, pkb is minus the log of kb. And remember, as soon as you put that minus in front of the log, you're changing the trends. So that means is that the stronger the kb, the higher the kb, the smaller the pkb. So in other words, the smaller the pkb, the stronger the acid. So when we look here, of all of these acids, C2H5NH2 has got the smallest Kb, so it's the strongest base, okay? And then this one here has the highest Kb, so that means it is the weakest base. So as the pKb goes down, the acid, or the base strength, excuse me, goes up. But we're not interested in bases, we're interested in acids. So let's put those two things together, shall we? The bigger the Kb, the weaker the acid. The bigger Kb, the smaller the pKb. So in other words, putting them together, the smaller the pKb, the weaker the acid. So the weakest acid is the one that comes from the base with the smallest pKb, which is C2H5NH2, which means that the weakest acid is C2H5NH3+. Okay. I don't know if this was a confusing way to put it, but it's important to remember these relationships. The Kb and the base strength related to each other directly, so the conjugate acid inversely. pKb and Kb relationships inverse, so the pKb and the conjugate acid related directly. Yeah, more of these things, and even sneakier here. I haven't just given you pKb's, I just say pK, because sometimes I give you a pKb, sometimes I give you a pKa. Now, if you look at the possible answers, NH3 is a base, pKb. C5H5N is a base, pKb. But ClO minus is a base that comes from HClO. BRO minus is a base that comes from HBRO, and NO2 minus is a base that comes from HNO2. So we've got to do some funny messing around. But ultimately, we want the weakest base. Weakest base is, of course, the smallest Kb and the biggest pKb. So what we're looking for here, seeing as how we got all these P's here, is ultimately the one with the biggest pKb. Let's go through them. NH3. Well, I already know its pKb is 4.75. C5H5N, I already know its pKb is 8.75. ClO minus comes from HClO, and the pKa of HClO, its conjugate acid, is 7.53. Well, pKa plus pKb equals pKw. In other words, pKa plus pKb is 14. So if the pKa of HClO is 7.53, the pKb is 14 minus that, which is 6.47. Same thing now for BRO minus, which comes from HBRO. pKa of the acid, 8.69. So the pKb of the base that we're interested in, 14 minus 8.69, 5.31. And finally, NO2 minus, pK of the acid is 3.37. So the pKb of the base is 14 minus that, which is 10.63. So ultimately, we want the weakest base. The weakest base is the one with the biggest pKb. Which one has the biggest pKb? NO2 minus. 2-minute solution has concentration of 1. Which answer correctly ranks in order of pH from lowest to highest? Well, let's see what we've got here. We've got HBr, we've got HF, NaCl, NH3, and NaOH. Let's just do that. HBr is a strong acid. HF is a weak acid. NaCl has got Na+, which is nothing, Cl-, which is nothing. They're both spectator ions, so it's neutral. NH3 is a weak base, and NaOH is a strong base. So increasing pH from the lowest, the best acid, to the highest, the best base, is actually this nice order here, exactly as we did it. HBr, the strong acid, neutral, weak base, strong base. Which following solution is not correctly described? 0.1 molar ammonium is chloride, acidic. 0.1 moles of lithium nitrate in 1 liter of water, acidic. And 0.1 molar aqueous sodium acetate would be basic. Well, ammonium chloride is NH4Cl. Cl- is a spectator ion, so therefore it does nothing. So what's interesting there is NH4 plus left. Okay, it's a cation, it's acidic. LiNO3, well, lithium is a spectator ion and nitrate is a spectator ion, so there's nothing left, so it'd be neutral. And finally, NaCH3COO, that's sodium acetate or sodium ethanoate. Sodium plus is a spectator ion, so there's an anion left, will be basic. So yes, ammonium chloride is acidic, indeed, sodium acetate is basic, but lithium nitrate is not acidic, it is neutral. So a two-part question of opposite sides of the same coin. Sodium acetate is NaCH3COO. Na plus is a spectator ion, leaving you with CH3COO minus. That's an anion, reacts with water and accepts a proton from the water. When it does that, what's left is OH minus. And of course, having accepted the proton makes its conjugate acid. In this case, from acetate, you get acetic acid. You could call this ethanoate, in which case this is ethanoic acid. Either way, you make OH minus, which is basic. Opposite idea, aqueous solution ammonium nitrate. Ammonium nitrate is NH4NO3. NO3 minus is a spectator ion, leaving you with NH4 plus. Reacts with water, donates a proton to the water, giving you H3O plus. And of course, when NH4 plus acts as an acid in it this way, it leaves behind its conjugate base NH3. Presence of H3O plus in the solution means it is acidic. Which volume has the highest pH? Given Ka, 5 of HCN, 5.8 times 10 to the minus 10. KCH3COH, 1.8 times 10 to the minus 4. So 0.1 molar CH3COH is a weak acid. CH3COOK, K plus is a spectator ion, leaving you with CH3COO minus, which is an anion, which is therefore a weak base. HCN is, of course, a weak acid. KBr, both K plus, Br minus are spectator ions, so it's neutral. And HCN is, of course, a weak acid. So which is the highest pH? Well, the only one that is basic. Which one has the lowest pH would also be a fun one. Well, CH3COH is a stronger acid than HCN, so therefore this would be the lowest pH because it's the most acidic. This is a fun one. Barium acetate, ammonium acetate, sodium acetate, acetate of course being ethanoate, ranking them from least basic to most basic. Well, barium acetate, BaCH3COO2 minus. Sodium acetate, NaCH3COH, and ammonium acetate, NH4CH3COOH. So the barium acetate has got 0.2 molar of the CH3COO minus because barium is a spectator ion. Sodium is a spectator ion, so this is 0.1 molar CH3COH. And then neither ammonium nor ethanoate or acetate are spectator ions, so in solution you've got NH4 plus and CH3COO minus. Well, CH3CO minus is a base. So here you've got two of those bases. And this one here, you only got one of the bases. And this one here, you've got a base, but you also have an acid as well. So which one is going to be the least basic? Well, the one where you got the acid in there. Which one's going to be the most basic? Well, the one where you've got not just 0.1 of a base, but 0.2 of a base. So ammonium acetate, because the acetate, or the ammonium is acidic, then sodium acetate, because you only got one of those basic acetates, and barium acetate, because you got two of those basic acetates. All right, this is a fun and extremely important conceptual one, which the following describes forward reaction, Bronsted-Lowry acid-base reaction, K value less than 1. Well, Bronsted-Lowry acid-base reaction needs an acid and a base reacting. So here's an acid, HA, and its conjugate base is A minus. There's another acid, HB, and its conjugate base is B minus. So let's react together the acid with the base, HA plus B minus. And after that's reacting, you're essentially just shunting the proton around. So the base turns into its conjugate acid, Hb, and what was the acid turns into its conjugate base, A-. Now let's look at the situation in which HA is the stronger acid. Well, if HA is the stronger acid, that means A- must be a weaker base. So what we got here is we got the stronger acid on the left-hand side, weaker base on the right-hand side. Well, let's throw in the rest of these things, shall we? If A- is the weaker base, B- must be the stronger base, and HB must be the weaker acid. So what you see here is you've got the stronger acid on one side. It's got to be accompanied by the stronger base. So the stronger acid and the stronger base on the left-hand side react together. They will push the reaction to the right. K is going to be greater than 1. So stronger acid plus stronger base going to the weaker acid and weaker base. K is greater than 1. So flip it around. If you have the weaker acid and the weaker base, if you write those on the left-hand side, stronger acid and stronger base on the right-hand side, the stronger ones will push the reaction to the left. K is less than 1. So looking at the possible answers, when you have the weaker acid and the weaker base on the left-hand side, that will give you a K value less than 1.